Yep, still nobody to post. Continue what I was doing last time about the methods for computing the QR factorization. Okay. So last time I was talking about, oops, gonna move this. Gibbons rotations. And so I'll very quickly recap those. Alright, so the idea is you have a 2 by 2 matrix G that is has this form. It's a cosine, based on a cosine sine pair. So c squared plus s squared is equal to 1. And you apply G transpose times a vector xy, and that gives you a vector where the second component is equal to 0, and r is going to be the magnitude of your original vector. And we have formulas for the cosine sine pair. So c is equal to x over r, and the sine is equal to y over r, and that does the trick. So this is a way of, it's kind of like row operations in Gaussian elimination for zeroing entries, except now we're doing so in an orthogonal fashion. So what I'm going to look at now is how to use Gibbons rotations to compute the QR decomposition. A is equal to Q times R. So Q is orthogonal, and R is upper triangular. And A is m by n. M is greater than or equal to n. Okay, let's see. So before I give the algorithm, I'll just give a general idea. So what you do is, you start with A, and you use Gibbons rotations in order to zero each element of A below the diagonal. So it's kind of Gaussian elimination-like in that you're reducing A to upper triangular form. So I have, but the thing is we have so many elements to eliminate, and we're actually going to start from, so we go, like Gaussian elimination, we start at the first column, do all that, eliminate all those elements below the diagonal, then to the second column, third column, and so on. But the difference is, Gaussian elimination, we start from the diagonal and work our way down. QR factorization, we start at the bottom and work our way up. And the reason for that is because Gibbons rotations are designed to work on a 2-vector and zero out the bottom element. So I'm going to apply a whole bunch of Gibbons rotations to A, multiplying on the left. So when you multiply by Gibbons rotation on the left, you're rotating rows. If you multiply by one on the right, you're rotating columns. So here we're rotating rows. So the first element I'm going to get rid of is in row M, column 1. And then apply another one. That's row M minus 1, column 1, and so on. And I'll keep doing this until eventually I zero out row 2, column 1. So I apply M minus 1 Gibbons rotations, and all of this is meant to zero all the subdiagonal entries in the first column. And then I carry on to the second column, again starting from the bottom and working my way up towards the diagonal. And this process continues until finally I get to the very last entry that I want to zero out. And that's going to be in column N, row N plus 1 transpose. So I apply all of these Gibbons rotations, and each one is very cheap. So all I have to do is each one of these rotations just affects 2 rows of A. So I'm replacing each row by a linear combination of both rows. But I have so many row rotations that I'm applying that are I have order m times n of them. So it's still a lot of work. And the result of all this is my upper triangular matrix R. So it has an n by n upper triangular matrix at the top, and then if m is greater than n, I have several rows of zeros. So this is how I compute my QR factorization, and once I've done all this, I can accumulate all of these Gibbons rotations in the opposite order on the right. So I start with identity for Q, and then as I apply these rotations on the left to A, I apply them on the right to Q. So the accumulated product of all of these column rotations, accumulating them all to identity, gives me the matrix Q. So now I have my QR factorization. All right. So any questions so far about the general setup before I give the actual algorithm? Now, oops, here's this line. Okay. So now write this out in a MATLAB-like pseudocode. And I'll have to check on this, but I believe I have this posted on the site as gibbonsqr.m that implements this. So as I described, Q is initially identity, and then R is initialized to be equal to A. So now I'm going to do all my work on R, and then I'll be modifying Q as I go. Yes?
Did you say that's Gibbons QR times M or dot M?
Oh, dot. It's a MATLAB file name.
Okay, gotcha. Thanks.
Okay, so what I do is I loop over all the columns going from left to right, and then I loop over the rows starting from the bottom, going all the way to the row immediately below the diagonal. And then I have a function, and this function is also posted on the site, Gibbons, that gives me a cosine-sine pair. And the thing is, what I have to give it is my vector xy that I want to rotate so that its second entry becomes 0. So the idea is, the entry I want to eliminate is R, whoops, that should not be M, that should be I. I is my row counter and J is my column counter. So I'm in row I, column J. That is the entry that I want to be eliminated. So this entry is going to go to 0. And the entry I use to eliminate it is the one that's directly above it. So I minus 1 J. Okay. So in the notation of the previous board, this is X and this is Y.
So should your I go from M to J?
Yes, it should. I knew there was an M in there somewhere. was reading my notes. So, okay, yes, M by N matrix. Well, at least the notes are right. Okay, and then I'm going to define this matrix G that works with zeroing an element ij and uses a given cosine sine pair. And I described this matrix last time, where if you look at it, so in this case, I is always greater, actually, yeah, I is always greater than j. Oh, wait a minute. In this case, what we're actually using is, oh. Alright, there's a mistake in the notes. I just haven't written it here yet. Okay. So we put the cosine sine pair here in the ij position. So ii, ij, ji, jj. And then the rest of the matrix is identity. So 1's up to here, 1's in between here, and 1's down here. And everything else is 0. So we're embedding this 2 by 2 Gibbons rotation from a previous board and embedding it in an identity matrix. Okay. So this is the kind of matrix I'm going to use to wipe out this element in position in row I, column j. Okay. So not quite what I wanted here. I'm having a notation issue. Because all I really want to do is rotate rows I minus 1 and I. So, okay. In fact, okay, I'll have to change this in the notes later. So yeah, this part of the notes is wrong. In fact, just to make things a little less painful, because all I'm going to be doing, I'm always going to be rotating 2 consecutive rows. Okay.
What part of the notes is wrong?
What?
What page or part of the notes?
This is page 139.
Like a matrix or something? Is that what you're talking about?
Of a matrix I
'Cause
described
there's no-
earlier.
Yeah, that's that.
Yeah.
We use sigma and gamma
Yeah.
instead.
But, yeah. Well, the
Okay.
Greek counterpart to CNS.
Right.
Yeah.
Didn't know that.
What?
Gamma is F.
The gamma is C.
Yeah.
Alpha, beta,
This
gamma.
is the third.
Okay. Okay. Because what I need to do is I'm gonna, just to make clear that I'm only working on rows I minus 1 and I, that the rest of the matrix is not going to be affected. So I'll use some MATLAB-like notation. So rows I minus 1 to I of R, and the entire, actually I don't even need to work on the entire row. I can start from column J and go all the way to the end. Nothing else needs to be touched. And I'm going to multiply these 2 rows on the left by this Gibbons rotation. So, and then I'll overwrite these rows